Chapter 7 is about frequency modulation. We want to look at Chapter 7, frequency modulation. So let's start. The aim of this chapter is for you to know frequency modulation and how it can be applied in telecommunications systems. So you should be able to define the frequency modulation, know the advantages of FM over AM, and also be able to calculate these factors of frequency modulation. So let's start. Frequency modulation FM is widely used also in Zimbabwe. We talk about Power FM, Star FM. Our radio service providers use frequency modulation, as we'll come up with the term FM. So FM broadcast on VHF band still provide high quality radio. FM is also used for variety forms of two-way radio communication. The information to be transmitted is added onto the carrier by the process of modulation. We have already described modulation as the process of inserting information signal onto the carrier. So in this case, we also say that when we insert this information, we'll either vary the amplitude frequency phase of a carrier. So in our frequency modulation, what we are varying is the frequency of the carrier. The carrier is being varied in accordance with the amplitude of the modulating signal. So during modulation, the carrier frequency increases when the modulating signal increases. As you can see from this signal, when our modulating signal shown in red is varying, it also causes variation in the frequency of the blue wave. The blue wave is the carrier which has been modulated by this red signal. So an increase in amplitude causes the frequency to increase. A decrease in amplitude causes the frequency to decrease, as shown on that diagram. The amplitude of the frequency modulated wave remains constant. It doesn't vary. So which actually means that the power of this wave is also constant. It's just the same as the power provided by the carrier. Unlike in our conventional AM, we said that we've got three components. We've got VC, we've got the upper sideband, we've got the lower sideband, each having a different amplitude component. But in this case, we have got a constant amplitude, unlike in amplitude modulation where the amplitude is varying. So the total power contained in the wave is constant and is equal to the unmodulated carrier power. Now let's look at the advantages of FM over AM. The first one is we've got an improved signal to noise ratio, meaning that our signal has got lesser noise. Yes, interference can occur, but it is easy for us to remove noise in an FM signal. And also, it has got smaller geographical interference between neighboring stations. Also, because we can control the power of the carrier, we can transmit less power. Well-defined service area for a given transmitter. Unlike in AM, whereby we're seeing that there are several components in an AM signal, each having a different power level. But with our FM, we've got a constant power level, meaning that it is a particular transmitted power has got a particular service area which it can transmit to. So let's take, for example, we said that in AM, when it is modulated by several components, frequency component like that of a voice band frequency, it produces several components also, which makes the upper and the lower sideband. These components vary in terms of amplitude in a complicated manner. Unlike in our frequency modulation, we know our power is constant. Therefore, a constant power, we can actually map out the area in which that signal is going to transmit to. And then looking at the disadvantage, much more bandwidth, because now we are varying the frequency. We are not varying the amplitude. We tend to use much more bandwidth compared to the AM signal. We're also going to look at this when we are now calculating bandwidth of an FM wave. Yeah, it has got more complicated receiver and transmit. If you just search for, we looked at a demodulator of an AM signal, a diode detector. It's just a diode in the capacitor. It's very simple. In this case, we've got much more complicated circuit, even also complicated in terms of explaining the operation of those circuits. So those are the two advantages. So this is just an example showing our modulating signal with varying amplitudes. And then here we've got our modulated carrier, the carrier after being modulated by the signal. So this is the first scenario. Let's say we've got an unmodulated carrier of 3 megahertz. It means that that unmodulated carrier, we need 3 complete cycles in 1 microsecond to get a frequency of 3 megahertz. We need 3 complete cycles in 1 microsecond. So now 3 complete cycles of the unmodulated carrier will occur in 1 microsecond. So when at t is equal to 0 to t is equal to 1, at this point our modulating signal is 0. We do not have a modulating signal. So if we modulate 0, we should get the frequency of the carrier, which is just 3 megahertz. So we're taking from this point to that point. As you can see, we've got 1 complete cycle, 2 and 3 complete cycles for this. So it means that the frequency from 0 to 1 is just that of the unmodulated carrier. So let's look at 1 to 2. At 1 to 2, our amplitude increases from 0 to 1. So for 0 to 1, V is equals to 0, the frequency remains at 3 megahertz. At t is equal to 1 to t is equal to 2, that's where we are now. T is equal to 1 to t is equal to 2. We've got 1, 2, 3, 4. Now, for the same 1 microsecond, now we've got 4 complete cycles. So the voltage amplitude is 1. And then instantaneous carrier increases to 4 megahertz. The assumption is that we've got a sensitivity of 1 megahertz per volt, which means that we increase our frequency by 1 megahertz for every 1 volt increase. So that's the assumption. There are now 4 complete cycles of the carrier voltage. Now let's go to t is equal to 2 to t is equal to 3. This is the point. At that point to that point, our voltage is back to 0. So if we count the number of cycles, we've got 1, 2, 3. So it means that we've got 3 megahertz frequency. The modulating signal returns to 0. The frequency falls to its original 3 megahertz. Then to t is equal to 3 to t is equal to 4, our voltage is minus 1 volt. So we reduce our frequency by 1 megahertz from 3 megahertz to 2 megahertz. So the modulating signal is minus 1 volt. The carrier frequency is reduced to 2 megahertz. So at this point to that point, our frequency is now 2 megahertz. So when t is equal to 4 to t is equal to 5, our frequency should go back to 3 megahertz because we are back at 0. And then let's just go back a little bit. Here we've got 2 volts. 5 5 to 6, we've got 2 volts. Our frequency should increase to 5 megahertz. You can actually count 1, 2, 3, 4, 5. We've got 5 megahertz to this point. And then at 0, we've got 3 megahertz. And then because here we've got minus 2 volts, we've got 1 complete cycle, meaning that our frequency is at 1 megahertz. This is a more exaggerated example. You will find out this variation, they are just there to explain the function of an FM modulator. So in actual fact, we can have this type of signal. This type of signal is for a sinusoidal modulating signal, which is modulating a carrier, and you can actually see the difference in frequencies. Let's say it's an audio signal which has got varying frequency, varying amplitude like that. You can also see that the variations that are happening in the carrier are also due to the signal that we have there. So, FM of a sine wave, the carrier frequency is made to vary according with the instantaneous value of the modulating signal. The amount by which the carrier deviates from its nominal value is proportional to the amplitude of the modulating signal. This we have already seen. Now, let's look at some terms that are being used. First of all, we've got what we call frequency deviation. The magnitude of frequency variation to either side of the nominal carrier frequency is called frequency deviation. So let's go back a little bit. We looked at that example with the rectangular square wave, whereby the frequency vary from 3 megahertz to 4 megahertz to 5 megahertz, or 3 megahertz to 2 megahertz to 1 megahertz. That variation from 3 megahertz, or that change from 3 megahertz to 5 megahertz, for example, is called deviation. The variation from 3 megahertz to 1 megahertz is also called a deviation. So this is the magnitude of frequency deviation. So from the carrier, you can either deviate from the carrier to a certain value, or from the carrier to a certain lower value. So this is what we call deviation. It's the variation from to either side of the carrier frequency. It is proportional to the amplitude. When your amplitude increases to 1 volt, we increase the deviation from 3 megahertz to 4 megahertz. So there is no maximum value. You can actually deviate to any certain value. It is possible for an FM signal to deviate. But because of that, sometimes because one can deviate to either side, it doesn't mean that when you deviate to a certain value, you are deviating within your allocated bandwidth. Sometimes let's take for example, let's say we've got Star FM. Star FM frequency, it is possible for them to deviate entering into, for example, Power FM radio frequencies. So because of that, we end up limiting. So we've got what we call rated system deviation. This is the maximum value of frequency deviation which is permitted. We said it is possible to deviate either way, above or below the carrier, but there is a certain limit that is permitted for any particular system to deviate. A maximum allowable frequency deviation must be specified since the bandwidth occupied by an FM wave increases with increase in frequency deviation. Frequency deviation is directly proportional to the modulating signal voltage. So when we limit our deviation, we also limit the modulating signal voltage. So it sets a maximum allowable modulating signal that can be applied to an FM modulator. If you exceed that maximum allowable, it means that you are going to deviate beyond your specified bandwidth. So here we've got an example. We're given a frequency modulated system and a rated system deviation of 30 kilohertz. So this is the maximum deviation allowed. If the sensitivity of the frequency modulator is 4 kilohertz per volt, what is the maximum allowable modulating signal voltage? So in this case, we are given our deviation being equal to 30, and then our frequency modulator sensitivity is 4 kilohertz. So if we divide by this, we get 7.5 volts. So what this means is that for every increase of 4 kilohertz, we have an increase of 1 volt. So to see the total voltage that we can vary by, is just divide 30 kilohertz by 4 to get 7.5. This is the maximum allowable modulating signal voltage for this system, rated system deviation. Okay. Then we've got what we call frequency swing. It is the maximum carrier frequency minus the minimum carrier frequency, and it is equal to twice the frequency deviation. So we're simply saying that in our case, we've got our carrier here, and then our signal can deviate. So our carrier frequency can deviate above or below that carrier. So the swing, we're talking about the difference of the highest to the minimum deviation that occurs. So it will be, we say deviation is from the center going up or from the center going down. But for swing, we're talking about from this point to that point. So it will be 2FD. Okay, this is the swing. It's just an animation to help you understand the swing. So, modulation signal factor K. Most of the time, the amplitude of the modulating signal voltage will be less than the maximum allowable. We said that the maximum allowable gives you the boundary in which you should not exceed. But obviously, when you are modulating, your signal will be a little bit less than the maximum allowable. Let's say the maximum allowable is 7.5 volts. You can actually modulate using a 5 volts instead of 7.5. 7.5 is easy for you to exceed your maximum allowable. For example, by inserting a 7.7. So to be safe, you use a lower voltage to the maximum allowable. The frequency deviation of the carrier will be smaller than the rated system deviation. So K is the modulating signal voltage that you are using over the maximum allowable voltage. For example, if I use 5 volts and the maximum allowable is 7.5, it will be 5 divided by 7.5. So the frequency deviation of the carrier frequency is given by the product KFD. So if you, whenever, let's say you are given your K and you want now to calculate the frequency deviation being caused by your signal, given your factor K, you can actually calculate where FD is the rated system deviation. So here we've got an example. An FM system has a rated system deviation of 75 kilohertz, and this is produced by a modulating signal of 10 volts. Determine sensitivity. For your sensitivity is just 75 kilohertz divided by 10 to give you 7.5 kilohertz per volt. There are 7.5 kilohertz per volt. And then the next, the frequency deviation produced by 2 volts. The frequency deviation produced by 2 volts. So first of all, you can calculate your K. So K is equal to 2 over 10 to give us 0.2. Then the frequency deviation is therefore 0.2 times 75 to give us 15 kilohertz. That will be the deviation caused by 2 volts. Frequency deviation of the carrier is proportional to the amplitude. The modulation index will continuously vary as the amplitude or the frequency of the modulating signal changes. So we've got what we call the modulation index that we want to determine. So it says when the carrier voltage is frequency modulated, its phase also changes. Alright, any change in frequency causes a change in phase of that signal. So therefore, changes in the frequency in FM signal also contribute to changes in the phase of that signal. So the peak phase deviation is equal to the ratio of the. Now we're talking about frequency deviation. Now I want to talk about the phase deviation. So the peak phase deviation is equal to the ratio of the frequency deviation to the modulating signal frequency, and is called the modulation index. So it is given by FD, frequency deviation, over the modulating signal frequency. This will give us the phase deviation. So the phase deviation actually is the changes in phase of that signal. So what does it mean when M is equal to 0? When N is equal to 0. It means we have no modulating signal present. Our signal doesn't vary when there is no modulating signal present. The frequency deviation should be equal to 0. Remember, I'll say FD over FM. The deviation, it will be equal to 0, and so is the modulation index. Only the carrier wave with stable frequency FC is left. So that's when M is equal to 0. When M is not equal to 0, it means that there is deviation. And when there is deviation, we actually have modulating signal present. So with a modulating signal present, the modulation index actually changes. So the moment we have a modulating signal, there is bound to be deviation. And that deviation also causes phase deviation or phase changes of that signal. A change in phase of the carrier wave equals the same time a change in frequency of this wave. So whenever the frequency changes, the phase is also changing. So here we're given an example. We're given a carrier of 100 megahertz is frequency modulated by 10 volts, 10 kilohertz. So this is the amplitude, and this is a modulating signal frequency, FM. The instantaneous carrier frequency varies between 99.95 and 100.05 megahertz. Calculate the sensitivity of the modulator. So to this question, this is the solution. Here the peak frequency deviation. So frequency deviation is we're saying that our signal is deviating from 100 megahertz to 100.05 megahertz. So our deviation there, if you say 100.05 minus 100 megahertz, it gives us a frequency deviation of 0.05 megahertz. Therefore, for sensitivity, it is equal to deviation, this deviation divided by the modulating signal, which is 10 volts, to give us 5 kilohertz per volt. And then next, the modulation index. Modulation index is equal to FD, frequency deviation, which is this 0.05 over FM, which is 10 kilohertz. So 0.05 megahertz divided by 10 kilohertz gives us 5. That will be the modulation index. The modulation index gives us what we call the peak phase deviation. It is just equal to this value, and then we express that value in radians, which is equal to 5 radians. Okay, example 4, you can attempt it and then send me your solution. Let's move on to FM spectrum and bandwidth. All right, just like with the amplitude modulation, we may talk about the simplicity of adding two signals, but there is a much more complicated way in which we can explain what is happening by using the formulas. Whenever we place two signals together, there is actually a complication that can only be explained using formulas. So the bandwidth spectrum of and sidebands are of great importance when using FM signal. The sidebands of a frequency modulated signal extend to either side of the main carrier, which causes the bandwidth of the overall signal to increase. This we have already seen. We can actually vary the frequency of the carrier by varying the amplitude. As the modulation of the carrier will vary, so do the sidebands. So now let's look at the mathematical expression. Here we're talking about a single tone, which means one frequency signal, just like in our AM signal. Vm, this is an equal sign. Vm is equal to Vm sine omega mt. We've already discussed this equation in amplitude modulation. So we're mixing that signal with our carrier frequency. The mixing of this signal to the carrier signal gives us this equation number 3. We're not going to draw much on how it was derived, but you can actually see that the amplitude is Vc. We've got Jo mf sine omega ct J1 mf omega c plus omega m, omega c minus omega m, omega c plus 2 omega m, omega c minus 2 omega m. These are frequency components that are generated. These components that you see on this equation, they are just components that are generated when you mix the carrier and the modulating signal to form an FM signal. So it can be seen that besides the carrier frequency, a set of side frequencies are generated on a repeated distance of FM. The amplitude of the side frequencies, just like the carrier, depends on the modulation index MF and are determined by a coefficient Jn, the so-called Bessel function of the first kind and order. Okay. So now let's explain. This is modulation index. This is a factor of a formula known as the Bessel function. So you can actually see that this first component is the carrier component. It's JOMF sine omega CT. And this is more like FC plus FM. This is FC minus FM. And then this is FC plus 2FM. This is FC minus 2FM. And the equation is infinite, which means the next factor is FC plus 3FM and FC minus 3FM. The fourth one will be FC plus 4FM, FC minus 4FM. This is an infinite equation. So these are components that are generated in an FM signal. It is enough for you to know that this function exists and their values are different. For different modulation indices are known. So the Bessel function is gives us the spectrum or the relative levels of sidebands which can be obtained. So let's look. This is the formula. As you can see, FC plus FM, FC minus FM, FC plus 2FM, and so on and so on. This is the spectrum of the Bessel function. Now, this is how it appears graphically, where the red component is when J is equal to 0. So this represents the carrier. This represents the first order, which is FC plus FM, second order, third order, fourth order, and so on and so on. This is the Bessel function. As you can see, the amplitude also varies. This is modulation index, which means that at M is equal to 1, we have this component, that component, that component, and that component. And M is equal to 2, and so on and so on. So let's see how we apply it now. With increasing modulation index MF, more side frequencies are generated. As you can see, at 0, we only have this and that. Somewhere there, we've got this, this, and that. And then at this point, actually have this, this, that. All the signals are present here. The carrier energy decreases and even vanishes at modulation index is equal to 2.4. So let's come. 2.4 is somewhere here. The carrier is the red one. So you can actually see that this is the amplitude of the carrier. It decreases at this point. It actually becomes 0. And even for this, let's take the green one. At M is equal to 5.1, somewhere there, the green, which is the second order, actually decreases. And then the blue one, actually at 3 point something, 3.78, somewhere there, it vanishes. So the amplitude of the signal actually depends on the factor J. Jn is equal to 0, Jn is equal to 1, Jn is equal to 2. These are the side, the levels or the orders of the Bessel function. As the modulation index increases, it is found that other sidebands at twice the modulating frequencies start to appear. As the index increases further, other sidebands can also be seen. So let's take M is equal to 0.5. At M is equal to 0.5, let's go back to our modulation, to our Bessel function. At 0.5, we've got, at this point, we've got a carrier with an amplitude somewhere at 0.8 something at this point, or 0.9, I don't know, somewhere here. And then we've got this other component at 0.25 somewhere here, which is the first order. And then this one is nearly 0. So if we go back to the graph, you can actually see that we've got our carrier with this amplitude, and then this is the first pair of sidebands. And then if we move on to M is equal to 1, at M is equal to 1, you can actually see we've got those two components, which is these two is actually increased in amplitude compared to this one. And then also have another pair of sidebands. So let's go back and see. At M is equal to 1. At M is equal to 1, we've got this somewhere at 0.1. This one is actually increased in amplitude to this point. The carrier has reduced amplitude to 0.75. So we've got three components of the carrier, this and that, which is what we have on this diagram. And then at M is equal to 2, you can actually see that the carrier has got a smaller amplitude compared to this. And then we've got this pair of sideband plus another pair of sideband. So if you go back again to the Bessel function at 2, you can actually see that the carrier is below 0.25. And then we've got the greatest amplitude being given by N is equal to 1, which is the first order. Then we've got the green one, which is the second order. We have the yellow, which is the third order signal. And at this point, the purple one is almost equal to 0. So that's how as you can see, the bandwidth is actually increasing as you are increasing your modulation index. And then we've got M is equal to 4. M is equal to 4. At M is equal to 4, the carrier amplitude is even negative at this point. We've got a smaller component of this. We've got the black. you can actually see that we've got several components now on our m is equal to 4. So this is what we get. Because we're taking a modulus of the value, you can actually see the carrier is there. The first order is almost 0. We've got third order, we've got fourth order, fifth, and sixth order side frequencies. And the distance between the carrier to this is FM. The first order and second, the distance here remains equal to FM. So the distance between this one and this one is FM, this one and this one is FM. So this one is FM, 2 FM, 3 FM, 4 FM, 5 FM. And you can actually see that the bandwidth here has increased compared to the bandwidth at this point. So as you increase your M, the number of side components actually increases. And as they increase, the bandwidth also increases. So when a carrier is a frequency FC is modulated by a sinusoidal wave of FM, the resultant waveform contains components at a number of different frequencies as follows. We've got the carrier components, we've got the first order side frequencies FC plus or minus FM, second order FC plus or minus 2 FM, third order FC plus 3 FM, etc. etc. The number of side frequencies present in a particular wave depend on the modulation increase. A larger number of modulation index value, the greater the number of side frequency being generated. We actually saw that the difference between M is equal to 1 and M is equal to 4. The amplitude of the various components, including the carrier itself, vary in a complicated manner. As you saw on our diagram, the amplitude was varying. Any component, again, including the carrier, may have zero amplitude at a particular value of modulation index. So why is this important? It gives us what we call a narrowband and a broadband FM. Narrowband. So an increase in bandwidth gives us a broad bandwidth, a larger bandwidth. So for small values of M, MF less than 1, there are only 1 or 2 pairs of significant side frequencies. Like we saw, we only had the carrier and 1 set of side frequencies. This case corresponds to what we call a narrowband FM. Even like you saw, the bandwidth was small, so we call this a narrowband FM signal. So for values of MF far much greater than 1, the side frequencies cover a wide spectrum. For example, when we were at 4, the number of side frequencies were more than when we had MF being equal to 1. They show clearly that an increase in modulation index of an FM wave will result in an increase in number of side frequencies generated. When the number of side frequencies is greater than 10, the number of significant side frequencies does not depend very much on MF. It becomes more constant as you increase your frequency. So frequency modulation bandwidth is 2 delta F plus FM. Bandwidth is 2 delta F plus FM. This is the frequency of the modulation signal. Well, delta F here is just frequency deviation, FD. So this is FD plus FM. Unlike the case of modulation amplitude modulation, it was just 2 F, the highest FM. In this case, we add the frequency deviation. Whilst the same is true for narrowband FM, the situation is not true for wideband. So for narrowband FM, bandwidth is almost equal to that one of an AM wave. The required bandwidth can be very much larger with the detectable side frequencies spreading out over a large amount of the frequency spectrum. So here we're given, let's say FD is equal to 75 kilohertz and FM is equal to 15 kilohertz. So using the formula, we'll get, so for our bandwidth, we get 2 times 75 plus 15. So it's 2 times 90, which gives us 180 kilohertz as shown there. And then if it was AM, it's just 2 FM, we get 30 kilohertz. You can actually see that the bandwidth of an FM is greater than the bandwidth of AM, which is one disadvantage of an FM signal. The use of larger bandwidth leads to improved signal-to-noise ratio, which is an advantage. Yes, the bandwidth is large, but it improves our signal-to-noise ratio, which means that we can get a higher quality signal, FM, compared to the AM signal. Even though narrowband does not have this property of an improved signal-to-noise ratio, is only for a broadband FM. Okay. There are a few interesting points of summary relative to frequency bandwidth. The bandwidth of a frequency modulated signal varies with both deviation and the modulating frequency. It's FD plus FM, 2 times FD plus FM. Changes in frequency, in deviation plus the modulation index. Increase in modulation frequency reduces modulation index. It reduces the number of sidebands. Remember, modulation index is equal to FM over FD. So we say that modulation index is equal to FD over FM. So an increase in FM reduces your modulation index, therefore reducing your sideband. Increase in modulation frequency increases the frequency separation between the sidebands. Remember, the difference between one set of sideband and the next is equal to FM. The frequency modulation bandwidth increases with modulation frequency, but it is not directly proportional to it. Okay, so those are the key points that you should take note of. So to demodulate an FM wave, we need what we call a frequency demodulator. So the frequency demodulator, what it does, it just converts the variation in frequency to a proportional amplitude. Remember, we're doing the opposite of modulation. In modulation, we're taking the amplitude, converting it to variation in amplitude. In demodulation, we're taking the variation in frequency, converting it to variation in amplitude. So that's the modulation. In simple terms, in order to extract the modulation from an FM, changes in frequency must be converted to corresponding changes in amplitude. So these are the advantages of FM over AM. The range of modulating signal amplitude from the lowest to highest provided is higher. Selective fading is not a problem. Since the amplitude is constant for an FM wave, fading is not a major issue. And increased signal to noise, this is SN for a wideband signal, like we just explained. And also, our transmitter, we can use Class C amplifiers because of the high efficiency of Class C amplifiers, whereas in AM signal, a Class C amplifier cannot be used. We'll also explain this more when we're looking at the transmitter systems. The FM wave has a constant amplitude, and this allows each RF stage to be operated in optimum manner. An FM receiver has the ability to suppress weaker signals. So these are the advantages of the FM signal, and the major disadvantage is bandwidth, the increase in bandwidth. So this is the end of our chapter 7. For any questions, please feel free to ask. Thank you.